It's okay if you don't get all the details with this example. Real world stuff is obviously a lot harder than just a quick textbook um, academic example. And if you're doing this in industry, they would give you a week to nail down all the details and to actually build it. But here's the idea. Let's say that you want to build a small wireless CIA data transmitter. For those of you who didn't know, my background's in military intelligence. And you want to build a device, something that gives telemetry. You want to bury a device beneath someone's driveway, say, that measures how often vehicles every day drive back and forth. I think you can see why this would be so critical for operational security. Let's say that you were able to do this in a road outside a military base. And ordinarily on typical times, they have 6 vehicles driving in and out, or maybe if it's out of the motor pool, they have 60 vehicles driving in and out. And then all of a sudden it pops up to 240. And now you know that there's something going on. Let's say the military base is heavily controlled, as it probably would be. Then don't do it outside don't do it on the heavily controlled military base. Do it in the driveway outside a pizza joint that's close by. What you'll find is that when everybody starts working late at nights, they'll start ordering pizzas, and the delivery trucks will drive far more frequently. And you'll see a massive increase. If you've ever, we've done this before, and it works phenomenally well. And of course, you can't control the driveways outside every fast food joint, and fast food joints open up all over outside military planning operational centers. But you don't want to be always transmitting, right? Because if it's always transmitting, it's easy to find. You just walk around with a wireless sensor and you can find it. So instead, what you want to do is send a really short burst, one quick boom that sends the number. And if it sends it over a 1 second period once a day, you'll never find that. Also, if you send it one time a day, it uses almost no energy. So the thing of batteries can last you for years and years. And in particular, what you want to transmit is a 99% pure sine wave, and its frequency will tell you how many cars passed. So you want to make it tunable. You'll probably have some sort of microcontroller in it to measure these things. And you want to make that microcontroller create this frequency that's tunable between 100 kilohertz to say, let's say, to 110 kilohertz with 100 hertz accuracy. So the idea is that 100 kilohertz equals 0 trucks. 100.1 kilohertz equals 1 vehicle. 100.2 kilohertz equals 2 vehicles. And you can, all the way up to 110 kilohertz, which would be what, 100 vehicles. So this is a great example of something that uses almost no energy, is almost undetectable because it uses so little energy. You can make it into a small thing, barely. You can make the electronics in this in a microcontroller. You can embed that in something barely over the size of a nail. You put in a battery that's strong enough to transmit, say 100 feet, and that's nothing. That's a AA battery can handle something like this for a couple of years. And then 100 feet away, you have a much larger system that's in a more secure area that has a larger battery that can then send your signal up into space for satellite relay. Okay, so you want to build this thing. And so your try number one is you say, I know how to do this. I took EE230. I took electronics. I know how to build an oscillator. I'm going to build an analog sine wave out. You might have built one of these things in your electronics classes. Well, that's great. Our requirements are, is it a 99% pure sine wave? Check. That's easy. Is it tunable? That's hard to make a tunable circuit, right? Tunable analog. You've got to unsolder and resolder components in there. Maybe you could make something kind of complicated that has a microcontroller that switches capacitors and Rs in and out of your circuit. So maybe the microcontroller controls a relay that then controls these Rs and Cs switching out. So I'll say sort of here. It is possible to do, but you'd end up having a bunch of relays, which would make your system pretty darn big. Every relay takes a lot of space. And in order to get it to be tuned to any of those 101 different possibilities, you're going to have a lot of Rs and Cs in there. You'd have to have at least 10 different Rs and 10 different Cs. That's you're getting a big package. Can you get 100 hertz resolution? Well, 100 hertz resolution versus 100 kilohertz means you're going to have better than 0.01% overall accuracy, overall precision here. And overall means with all of your Rs and Cs combined. If you've got a bunch of Rs and Cs being flipped in and out, that means your individual capacitors will have to be better than 0.1% accuracy. That's not possible. Your best capacitors, your very best ones might be 1%, and even that won't be temperature stabilized. On a hot day or on a cold day, it's going to give you over a 1% variation. So the analog sine wave just won't work. So here's your try number 2. You're going to program your microcontroller to give a square wave. Now, that's easy to do, right? If it's a 10 megahertz clock, it means that you've got one accuracy you've got 1 equals 10 million clock cycles per second. And so you can do something like push out a high on pin 1, and then put the number 46 into your timer. And then you're going to count down your timer. Every single clock cycle will count your timer down from 46, 45, 44. And then once it's finished counting down, you'll put a 0 on pin 1. And then you'll put a 47 in your timer. And then you'll count down your timer. And then you will go to your loop, which is up here. And let's see, that would take a total of 1, 2, 3, 4, 5, 6, 7 instructions. I'm sorry, that'll take a total of 1, 2, 3, 4, 5 instructions, 6 and 7. You might have to, these numbers might not be exactly correct, but it's going to be awfully close that the whole thing you want to take 100 instructions worth, so that at 10 megahertz, it corresponds to 100 kilohertz. And now it's pretty easy to adjust these numbers up or down to change your frequency. Now let's see what we get out of an approach like this. So Is it a 90%, 99% pure sine wave? No way. It's a square wave. Is it, wow, that was bad handwriting. Is it tunable? Oh yeah, it's easy to tune. You just simply change a number. You don't need any external R's and C's. Is it 0.1% accurate? Yeah. Remember, it's controlled. The timing, this 10 megahertz, is controlled by a crystal oscillator. And a typical crystal oscillator is at least 0.001% accurate, if not more. So there's no problems with the accuracy. So the only problem we've got here is that we've got this square wave, and we need to convert it to a sine wave. By the way, practically the reason why we want it to be a sine wave and not a square wave is you know from your Fourier series that your square wave has got higher frequency harmonics all over the spectrum. Remember when we try to create a square wave out of a sum of sine waves, and we just kept on adding and adding and adding harmonics, and we never really got it to look like a perfect square wave. So that means that if you do send a perfect square wave, you're sending tons of harmonics. Now, if you're searching for this bug, you can search over any frequency area you want to, and if you're spreading harmonics all over the place, you're going to pick it up. Whereas if you send it on a perfectly tuned sine wave, if you don't tune into that exact frequency, you're not going to find it. So it's harder to find. It's also far more frequency efficient, energy efficient, because the environment that you're sending your signal, whether it's air or whatever else, it's going to have certain preferred frequencies which go through it the best, and they'll have other frequencies that it's opaque to. And so if you're wasting a lot of your signal over a frequency band space where your transmission medium is opaque, you're just losing all that energy. So that's the other reason that you want to have it a really good sine wave. So how do we get it a 99% pure sine wave? The answer is we use these techniques to take your microcontroller signal and to put it through a low pass filter. So we've got our square wave over here, and over here we've got our sine wave. And you firstly take that square wave and you take a look at the amplitude spectra. And the amplitude spectrum says we've got, if we've got a 0 or 1 volt square wave, we've got a 1.27 volt fundamental frequency, where that fundamental frequency is varying between 110, is varying between 100 and 110 kilohertz. And then we're going to have, it just so happens that this is its first harmonic, it's fundamental. Its second harmonic is 0. Its third harmonic is down to 0.477. Its next harmonic is 0. Its upper harmonics are present, but they're still lower. And so all we need to do is build this low pass filter that cuts it down. And to make it a 99% pure, we just need to cut this thing down. So this point at whatever this frequency is, which is at least 300 kilohertz, we want to make this point at least 1% of this. So it better cut it down to 0.00127. So you convert that into decibels. Use my program to figure out what order of filter has a cutoff at 100 kilohertz, but at 300 kilohertz cuts things down to whatever it is in dB of a linear gain of 0.127. You can figure that out, right? That would just be 20 log 10 of 0.0127. That would be it in dB. And then you just screw around with what filter order is necessary to give that to you. Maybe it's a 6th order, and then you build your 6th order Butterworth low pass cutoff frequency of 100 hertz, and you're done. Pretty cool. You've got those skills now to go out and to actually build stuff that people want and people care about. Okay. Any questions before I let you go? really nice work on your lab, guys. As I said, those are powerful skills that you can see from the examples I'm giving here that you'll use over and over in, I mean, I've used them as a grad student, I've used them in industry, and you can too. I'll see you next class.